Exponential growth is how populations expand, or rumors spread in high school. It starts small and suddenly explodes. Mathematically, it has the form of a base raised to a variable. The key is that the variable is in the exponent. If the base is greater than 1, it grows like a social media trend or the number of infected people during a virus pandemic. If the base is between 0 and 1, it decays like your confidence after slipping on ice and landing face first in front of your crush, followed by an awkward thumbs up and internal screaming. To graph a basic exponential function like 2 to the x, just plug in a few values for x, calculate the outputs, and plot the points. You'll quickly see the shape. It climbs fast on the right and approaches the x-axis on the left. Plugging -1, 0 and 1 gives you 1/2, 1 and 2 respectively. That alone is enough to sketch the curve. And don't forget, it never touches the x-axis. It just gets closer to it forever. In a situation like this, we say the x-axis is a horizontal asymptote of the function. It must be frustrating, ever getting closer and never touching. It's like living with an AI partner. You get clever responses, emotional compliments on your beauty and intelligence. But no matter how close you get, there's still a cold, digital asymptote between you and your AI partner. Euler's constant is called the natural base because it shows up naturally in more advanced problems of economics, probability, calculus, and other such terrifying subjects. But let's be honest, it looks anything but natural. The first time I saw 2.7182818 on the board, I thought, this has to be the most random number ever. I was sure our math teacher was trying to prank us. So I understand if you have doubts, but trust me, the universe loves irrational numbers like pi, e, and root 2. The term logarithm was coined by John Napier in the early 1600s. Believe it or not, he created logs to make life easier, especially for scientists and engineers who had to multiply giant numbers by hand. But today we have calculators. So why do we still learn logs? Because math teachers have bills, too. And nothing guarantees job security for a math teacher like logarithms. Here are the basic properties of logarithms, which, frankly, sound like logs just complementing themselves. They're just stating the painfully obvious in fancy math language. If exponential functions are all about explosive growth, then logarithmic functions are about diminishing, forever slowing down growth. I am sure you have heard of learning curves. Unfortunately, these curves are logarithmic. That's because early progress is fast, but as you learn more, improvements get more and more difficult over time. It's like trying to go up by walking on a hill that is getting flatter the higher you go. This is also true about your progress while doing math homework. At the beginning you are fresh and progress is fast. Over time, each new problem takes more effort, your progress plateaus, and suddenly you're watching cat videos instead of studying logarithms. Logs are picky eaters. They don't do zero. They don't do negatives. To find the inverse of a logarithmic function, isolate the log and then convert it into an exponential expression, isolate x and finally swap x and y. To graph log x base 2, first accept that it's not in a hurry. It grows painfully slow. Start by plotting a few points. Log 1 is 0, log 2 is 1, log 4 is 2. That's about as exciting as it gets. This graph rises like it's absolutely exhausted. There's also a vertical asymptote at x equals 0, basically the y-axis, which it never touches. It's like that AI partner we discussed before. So sketch the curve rising slowly on the right, plummeting to negative infinity on the left, and remember, it may be slow, but it never stops trying. Last time we went camping, my wife asked me to bring natural logs. I didn't understand what she really meant. I just packed my calculator and a fresh stack of natural log problems. Turned out, she meant firewood. Let's just say, my calculator and I both slept outside. Graphing an exponential function and its inverse is actually kind of magical. You don't have to start over. Just take points from the exponential and swap the x and y values. Now you have points from its inverse. Also remember, graphs of inverse functions are reflections of each other with respect to the line y equals x. These equations turn into simple linear or quadratic equation once you have taken their masks off and exposed their common base. And just like that, the mystery disappears, and all that's left is good old algebra cleaning up the mess. We all agree that a logarithmic equation looks like a cryptic message in a spy movie. It's vague. No worries though. You have the skills needed to convert it into normal language, which means rewriting it in exponential form. Once you do that, it's just a regular equation, usually linear or quadratic, sitting there waiting to be solved. But remember, don't forget your domain restrictions. You must verify your answers in the original equation. Otherwise, you'll think you've defused the bomb, and then realize too late that the log never accepted your answer. In 1899, Parabellow was trying to explain to his students why a population growing by a tiny 0.01% per year is still technically explosive. One student called it boring. He calmly said, "So is dynamite before the fuse is lit. A slow-growing exponential is still exponential. Just be patient."